cloud. Great. So today we're talking about correcting our GPS, our RTK GPS surveys using the CORS system and Opus. First, we'll explore the National Geodetic Survey's continuously operating reference stations, CORS. These are GPS receivers that are basically permanently monumented, and they're giving you a highly accurate tracking of their location. And we use those monumented locations to correct our own survey within them. We'll apply this knowledge and use the National Geodetic Survey, so NGD online tools to correct our surveys. And we'll use Trimble Business Center to import and process GPS data. So just to repeat, we're correcting our survey when we're creating a new control point. If we're setting up our base station over a previously surveyed, highly accurate control point, we don't need to do this correction. This is only when we're doing a new survey, a new control point, new base station setup. So to review the geoid situation here, we have a geoid that represents mean sea level across the globe. That's this blue dashed line. We have the ellipsoid, which is this smooth ellipsoid that's fit to our planet, WGS 83. And whenever we take a GPS measurement, it gives us our elevation based on our ellipsoid height. How high are we above the ellipsoid? However, to make our GPS surveys more accurate, our elevation data more accurate, more comparable across the globe, we correct using the geoid height. And so our true height, which is big H, is approximated as the ellipsoid height minus the geoid height. Now, in this case, the geoid height is below, right, the ellipsoid height. So it's negative everywhere in the conterminous US, meaning the mean sea level is going to be below the ellipsoid. That's not the case everywhere. So we end up with basically reducing the ellipsoid height using the geoid. It's based on mass, surplus mass. The geoid surface rises above the ellipsoid where there's surplus mass, or there's deficit mass. The geoid is below the ellipsoid. So deficit of mass means that there's less dense material. So I'm assuming that continental plates are less dense than oceanic crust. So because it's less dense, then water isn't as attracted to it. So water will pile up and be higher where it's more dense. You can kind of think of it as the gravity is kind of sucking the water to it. In Alaska, maybe the crust is just more dense. It's surrounded by sea, etc. I'm making that up, but who knows. So here's just a graphic of that. The geoid is this funky shape representing the natural sea level. Here's our ellipsoid. Sometimes the ellipsoid is above, sometimes it's below. Geoids are typically country specific. Right now, Geoid 12B, we actually have Geoid 18. And then in 2022, there's going to be another update. Here is Geoid 18, and the geoid height is the difference between the geoid model and the ellipsoid. And so you can see that it's negative everywhere in the continental US. In Colorado, it is much more negative. I'm assuming there's some Rocky Mountain influence here. And so the ellipsoid again is this smooth shape. The geoid height is representing the difference between the mean sea level and the ellipsoid. You can see that this is a raster, right? There's contours drawn on this. If you zoom in, it's probably, I think it's on the order of a kilometer by a kilometer. Yeah. Right. Yeah, you would think it would be more dense. Oh yeah. So okay. because the Rocky Mountains are more dense, the geoid height is less negative, and so mean sea level is actually closer to the ellipsoid height. Where we have less dense material out here, a lot of sediment, right, alluvial stuff, glacial outwash, less dense. This is granite and really dense rock. So it's less dense, the geoid model falls farther below. I feel like I understand. Okay, so if we have an older geoid model that we did in a GPS survey 10 years ago, it's geoid 99 or something like that, then we can update it. So we can update the GPS height. So now there's a lot going on here, right? The geoid helps us correct our elevation. Our elevation is based on a vertical datum. And we talked about this in the previous lecture. The vertical datum right now is North American vertical datum, NAVD 88. And so what I'm saying is our elevation in this vertical datum, and do you guys remember where that vertical datum is based out of in that lecture? There's a vertical datum, basically it's tied to mean sea level in Newfoundland. You remember that? And then they took that mean sea level of Newfoundland and basically spread this system of leveling all the way across the continental US. That's what it's based off of right now. We're going to get away from this, and it's all going to be satellite based next year. All right, so we take our vertical elevation information. So all of our survey data is going to have that Z component from the old geoid. We subtract the new geoid height out, and we add the old geoid height, and then that will do the correction. So it's just some basic arithmetic. So we end up with new ortho height is based on old ortho height minus new geoid value plus old geoid value. And this tool right here will help you do that. So there's a way to correct. Having all your surveys in the same geoid is really important. A review of datums, the North American datum of 83. This is a geometric or XY datum that measures our position on the ellipsoid model of Earth fit to North America. It's a horizontal datum. And then we have this vertical datum, North American vertical datum 88. And it ties all of our vertical values to the mean sea level value measured in Newfoundland, right across from Maine. All right, let's bring it back to our GPS. We have control points. Why do we need control points? Why do we care to have a control point on our survey site? A monumented thing, a rebar, something that's semi-permanent. We need to come back to it, right? So Justin's working on the highway project. Every day they go out there and they set their base station up on a control point. That way they know they're working off of the same elevation from yesterday, the same XYZ from yesterday. So that base station sets XYZ and everything is relative off of that. So if we have the same XYZ base station, then we can go out and make sure our road elevations are going to match what they were from yesterday and the day before, and make that continue that nice smooth grade, whatever that design looks like. So again, we have two options. We can occupy an existing control point, the one that we used yesterday, right? Or the one from last year when we came back to the site. Or if it's a new site, we want to set up a new control point. That's when we set up our base station. We set the point up in the base station. And that's really kind of a critical step. We name it. We usually name it 100 if we have one control point. And if we don't know where it is based on a previous survey, then we press the here key in our Trimble unit, and it will give you a very rough XYZ location. Then the base station sets up over that point for many hours. To get a really good control point, you need at least about 6 hours, 6 to 8 hours. And every second it's getting XYZ, XYZ, XYZ. And you could plot those and it'd be this big cloud around that point. Now, what we're going to do today is use this system called Opus to correct that location based on the nearby cores station. So there's continuously operating GPS stations are all over a continent, and they're going to send us corrections that we'll use via an internet server to get a really accurate location for our point. Now, we do have existing control points all across the city. And this is what they look like. You can actually go to Mesa County and go on this website and find them. There's one nearly on every intersection. Maybe we'll get to go out and find it. And so it's been certified by a surveyor. It's got the coordinates in it. And you can set up your base station on that and use it to do a survey. That's best practice. Use an existing control point. Right? So it's called Professional Licensed Surveyor, PLS, and it's a separate track. Yeah, some civil engineers will get their professional survey license, but typically it's someone who just does surveying. Yeah. I think you probably end up, through WCCC, there's courses in surveying, and so there's a whole program. It's a little bit more than just on-site training. Yeah. But yeah, you could pull it off. I believe in you, Edgar. All right, so when you press the here button on your GPS survey, we're creating a new control point. We get a very rough estimate of our location. You can press it every second, you'll get a new value of XYZ. Yeah. Yeah, that's what we did outside. And that is based off of SBAS, so satellite-based augmentation system. It's basically plus or minus 1 to 2 meters accuracy. So we have to correct our base station's position using what's called Opus in post-processing. So Opus, we can access it through the National Geodetic Survey website. We can also do it through Trimble Business Center. So Online Positioning User Service is the acronym. And we give it our GPS data from the base station. It takes information and corrections from the surrounding cores stations and gives you a post-processed accurate XYZ position. So here is our cores network across the country. And here's Colorado. You can see there's a nice cluster in Mesa County. That's by some pioneering work from the survey group that's located here in this county. And these stations are based on how often are they collecting information, from 1 second all the way down to 30-second rates. And they're just sitting there year after year collecting information. They know after a certain point exactly where they are. The satellites are telling them where they are as well, based on the signal, right? And based on the difference of their known location, they've been surveyed in on the ground, and the GPS signal, they can calculate what the actual error is during the time of your survey. So error is going to change based on the constellation of the satellites, the ionosphere conditions, the weather, etc. And so when you do your survey, they know what kind of the general background error is, and then they can update your accuracy point by point. So the core station can be used for a lot of things. It's using for data correction. It's also being used for tracking continental drift. This is showing the movement of our continent over time. XYZ direction as well as Z. So the colors are Z. Mostly our continent isn't moving. Up here, there is uplift. It's called isostatic uplift. Does anyone know why it's uplifting in Canada? That would be sweet. No, I don't think there's any volcanoes up there. So what's happening? This is Canada right here. The glaciers retreated about 12,000 years ago. Glaciers were super heavy, and then they retreated. It's basically taking a huge weight off of the continent. So you get what's called isostatic uplift. The continent is slowly pushing back up from the mantle, right? The mantle is this kind of semi-fluid down below. And so after that huge weight was lifted off, it's slowly rising over time, over really, this is about 15 millimeters per year. We have subsidence in Texas and California. This is from groundwater pumping. Louisiana as well. Isostatic uplift in Alaska. California is shipping its way out into the ocean. That's the San Andreas Fault. Yeah, going to be an island soon. Hawaii is zooming in this way. All right, so there's two kinds of Opus solutions. There's the static solution. You need, it says at least 2 hours. I say 6 to 8 because you can kind of see how it flattens out over here. What this is showing is how long do you have your base station set up over your control point, collecting the information every second from the satellites. And it shows how our solution, root mean square error, is changing in centimeters. So if we only set our base station up for 20 minutes, we're going to have about 6 centimeters of error. We can bring that down to about 1 centimeter if we leave our station up for somewhere around 6 to 8 hours. So that's where that number comes from. So you want to try to leave it out there all day. Rapid static is a different kind of solution process, and you need anywhere from basically 30 minutes to 2 hours for that. So at most, you get about 2 centimeters of accuracy. So if you're pinched for time, you can do that. It's a different kind of solution. So our static solution, at least 2 hours. Best practice is 6 to 8. We get a better model of error and better correction over time. You also want to wait to submit to Opus the next day or 1 week later, even better. That's because it's had more time to kind of post-process. The system's constantly creating these error models and giving you better solutions. So you can't just do it the same day. You have to come back later after it's had time to kind of crunch the numbers. Yeah. The correction will be on the order of meters because your original base station, XYZ, was super rough, plus or minus 2 meters. So when you correct it, and we'll do it in class, it's going to snap over to the corrected location in the XYZ. Your solution is going to be accurate in the plus or minus centimeters, like 1 to 2 centimeters, but it's going to move your really rough point over quite a bit.
All of the rest of the data that
It all happens automatically. So we'll see in Opus, or sorry, in Trimble Business Center in a second. All of your survey points from your rover are vectors off of the base station. Also, it's all relative to the base station. So when you shift the XYZ, all those vectors are going to shift XYZ as well. So it's an automatic update. It's pretty slick. Here's the workflow. I just wanted to document it for you so you can always go back. Just very briefly, there's a T02, maybe it's T03 now. It's always updated. This is a file that your base station collects on Trimble. So T for Trimble. And it stores the information. It stores the elevation of your Trimble unit from your control point when you enter that in, when you create that point, right? And it also collects every second XYZ information from the satellites. So it's a really important file. You can download it from the base station using your controller, using Bluetooth or a USB thumb drive sometimes. Maybe not. I think it's just Bluetooth. All right. You download that file. You have to convert it to what's called RINEX. RINEX is a universal base station file that Opus website can use. Trimble Business Center can convert this for you. Okay. We can go to the Opus website. We can also do the workflow through Trimble Business Center. We have to know what kind of antenna we used. So this is Trimble TRM R10. And then we enter the reference height. And that is, what is the height from your units, basically antenna reference height down to your point. So we'll look at that. If you're using the website, you can put your email address on and it'll email you the solution in a little bit. You have to choose either rapid static or static based on how long your survey was. And these are two different kind of algorithms or methods for calculating the correction. Here's the website. Here's where you upload your file. You tell it what kind of antenna you're doing, and then give it the antenna height above the reference point. This is really important. This is where you go back and you documented everything. You did your sketch. Okay, it was 1.415 meters to the extension lever. And then we know that it's 0.01 meters to the quick release, and then 0.075 or whatever, to the bottom of the antenna. So understanding what the reference point is really important, because you're going to have to do all that math to do it. So here is our Trimble R10. These drawings are actually on Opus's website. The bottom of the antenna is the reference point. And here's the quick release height, so you might need to add that on. Here is a different antenna. This is a Zephyr 3 that we use for these different units that we have. And the reference is based on this bottom location right here. And here's our R8 units. And we're measuring to the bottom of the R8. What this is showing is how high you get to the antenna reference point. The antenna reference point, the antenna phase plane is exactly where the GPS signal hits the antenna. And this stuff is really in the weeds, but it's important because that's the distance, right, from the satellites all the way to your antenna point, which then is connected all the way to the ground. All right, so we'll do this. So this website is one way to do it. It's a little bit more clunky. If you have Trimble Business Center, which we do, we actually have a workflow that we can use. You can access it through this website and also through Trimble Business Center. So once you get a solution, you'll get it emailed back to you. It's going to be an XML file and a text file. Then it's got a lot of good information in it. So we open up the text file and let's take a look at it. It shows you your survey. So this is when you started. This is when you stopped. So we had about a 20-minute survey here, looks like. So this would be a rapid static solution. Here's our antenna. Here's the height to the antenna reference point. This is all information we want to double check. And then it gives us our corrected information. So here's our X, Y, Z in meters, and then lat and long as well. It gives us our ellipsoid height, and then our orthometric height. And this is what's the corrected height based on NAVD 88 using Geoid 18. It shows us how many observations did it use. It had 1,500 observations. It used 88% of those, meaning it threw some out. Some of them were just poor quality for whatever reason. You want this number to be about greater than 90%. The longer the survey you have, the more likely you'll get that kind of accuracy. Here's our corrected coordinates. And that's the accuracy. So you can see that these are accurate to, in this place, we have about 6 millimeters in the lat and the X and the Y. Actually, if we look at these this is probably a little more. So we have about 1.5 centimeters, 4.7 centimeters, and then about 4 centimeters. These numbers would improve with a longer occupation time. It shows you the corrections that it used. So these are all the core stations. There's one in Colburn, Mesa County, Nucla, Glenwood Springs, Montrose, Rifle. So these core stations are all over, and these are the stations that they use. So we had a lot of good coverage, right? All right, and this is just the basic details that we need to look at for Opus solution. We want to have 90% of observations. We're going to double check our antenna type and ARP height. And then we want to have overall root mean square error less than 3 centimeters for a static solution. All right, so now next step, we're going to do this together. So I'm going to stop the recording.